Hello, today I'm going to show you how the I2C protocol works. The Inter-Integrated Circuit Bus is a two-wire serial interface originally developed by the Phillips Corporation for use in consumer products. It is a bi-directional bus that is easily implemented in any integrated circuit process and allows for simple inter-integrated circuit communication. Connections are minimized by using a serial data line SDA, a serial clock line SCL, and a common ground to carry out the communications. The I2C Bus uses only two bidirectional lines, serial data line and serial clock line. I2C compatible devices connect to the bus with open collector or open drain pins, which pull the line low. When there is no transmission of data, the I2C bus lines idle in a high state. The lines are passively pulled high. The transmission occurs by toggling the lines by pulling low and releasing high. Bits are clocked on falling clock edges, and the standard data transfer rate is 100 kilobits per second, while the fast mode transfer rate is 400 kilobytes per second. The I2C bus can support multiple devices, both the slave and master, and the only limitation is the capacitance on the bus and the address space, which is 128 unique addresses. I2C data packets are arranged in 8-bit bytes comprising slave address, register number, and data to be transferred. Transmission over the bus is either a read or write operation. The reading and writing protocols build upon a series of subprotocols such as start and stop conditions, repeated start bits, address byte, data transfer bits, and acknowledge not acknowledge bits. As the name suggests, a start condition always occurs at the start of a transmission and is initiated by the master device. This is done to wake the idling slave devices on the bus. This is one of the two times the SDA line is allowed to change state when SCL is high. To signify a start condition, the SDA line transitions from high state to low state, while SCL is high. Similar to a start condition, the stop condition occurs at the end of a data transfer and is also generated by the master. This signifies the end of the transfer and is a command to tell the slave devices that they should go back to an idle state. Release the SDA line and not send any more data on the bus. This is the second instance where the SDA line is allowed to change state when SCL is high. The SDA line transitions from low to high state, while SCL is high to signify a stop condition. In all other conditions, the SDA line only changes state when the SCL line is low. A slave address is sent in 8-bit byte format, MSB first, but the last bit signifies whether the transaction will read or write to the slave. In effect, the upper 7 bits constitute the slave address, while the 8-bit served as a read or write command bit. Thus, there is an address space of 128 unique addresses for addressing up to 128 slaves. For example, following a start condition, the master sends an address byte which corresponds to the unique address of a slave device on the bus. The devices on the bus each have their own fixed or programmed addresses. The slaves on the I2C bus respond to the start command by actively listening to the first 7 bits of the first byte sent. If the first 7 bits match the slave device address, it continues by reading the 8-bit of the address byte. All other slave devices ignore the remainder of the transaction. A low in the read-write bit specifies that the master will write data to the address the slave device, and for a high, the master will read data from the slave device. Once the address byte has been read by the corresponding slave, it will acknowledge this transfer by sending an acknowledge bit by pulling SDA low for the adjacent clock high pulse period, and then assume the role of a slave transmitter or slave receiver depending on the read or write bit sent. From this point onwards, unless a stop bit is sent, the slave assumes that since it has been already addressed, all communication is being directed to it. As a form of feedback, after every byte transmission, the receiving device sends an acknowledge or not acknowledge bit. An acknowledge bit is generated by the receiver by holding the SDA line low during a high SCL period, while a not acknowledge bit is generated when the receiver leaves the SDA line passively pulled high and does not respond in any way. This fact implies that in response to an address byte, all unmatched slaves send a not acknowledged bit by not responding. An acknowledge is used to denote that a byte was transmitted and received successfully, and that the transmission can continue on to the next byte transfer, a stop condition, or a repeated start. A not acknowledge is generally used by the receiver to indicate whether an error occurred somewhere in the data transmission. This is used to signal to the transmitting device to terminate the transmission immediately, or to make another attempt by sending a repeated start. A master will also send a not acknowledge after the last byte of the transmission it wants to read from a slave to indicate that the slave should stop transmission. Data bits encode the actual transmission data and are transmitted in 8-bit byte format, starting with the most significant bit, and each bit is synchronized with the clock signal. There is no limit to the number of bytes in a transmission, but each byte must be followed by an acknowledged bit which is generated by the recipient of the data. For a bit transfer, the data on the SDA line must remain stable during a high clock period. The data line is allowed to have a high or low transition only when the clock signal is low. Thus, the receiver reads a data bit on the data line while SEL is high, and the transmitting asserts each new data bit while SEL is low. This figure shows a master transmitting, addressing and writing data to a slave receiver with a 7-bit address. The first bit sent is the start bit which initiates communications. The address byte follows on subsequent clock pulses. At this point in time, all the slave devices on the bus are listening for their device address, which makes up the first 7 bits of the address byte. The slave device that finds an address match continues to listen to the last bit to understand whether the master wants to read from the slave or write to it. All other slave devices ignore further communication by sending a not acknowledge, which by definition does not do anything. In response to recognizing its address and the right command, the address device responds by sending an acknowledge bit as feedback to the master that a slave device with the correct address is present on the bus and awaiting further communication. The master then proceeds with the data transfer by sending data in byte format. If the master is writing to a specific register in the slave device, then it writes the corresponding command byte prior to sending the data. After each byte transfer, the slave responds by sending an acknowledge. When the master is finished transferring all the data, it terminates the transfer by sending a stop condition. This figure now shows a master addressing a slave and attempting to read data from it. The transmission is again initiated by the master with a start condition, after which the address is transmitted on subsequent clock pulses. The address device continues to listen to the transmission by reading the read-write bit and responds with an acknowledged bit. Once the slave sends the acknowledgement, it assumes control of SDA and sends data to the master. In response to each byte it transmitted, the master sends an acknowledged bit, and when the master no longer wants to receive data, it responds with a not acknowledged after the last byte it wishes to receive, and then resumes control of the bus and sends a stop condition to end the transmission. Note that while control of the SDA line is passed around from master to slave and back, the SEA line is always in control of the master. Data is being clocked in and out by the master at all times.